Hi, and welcome to the Appalachian State University 2022 Solar District Cup pitch presentation. This year, we were assigned Cheyney University of Pennsylvania as our use case and have developed an effective collection of PV sites and a battery storage system for the campus. Our team is made up of 11 active graduate and undergraduate students and one faculty advisor from the Sustainable Technology and the Built Environment Department in Appalachian State. We divided the team into 4 working groups, one for each part of the competition: conceptual design, distribution analysis, financial analysis, as well as construction development. Each team member was able to choose which working group they were to work with, and I'm now going to hand it off to Grace for conceptual design to explain the goals and constraints we face within the Cheyney University use case.
So we went into this project with 3 overarching goals. We wanted to design efficient PV solar sites on campus that align with Cheyney University's climate action plan. Secondly, we aim to develop infrastructure for the university that allows them to integrate sustainability and renewable energy into their education programs. And finally, we hope to engage the campus community in the sustainability.
I can hear her, Eric.
Yeah, Eric, I'm getting her.
Can you hear me? Is that okay? We wanted to design efficient PV solar sites on campus that align with Cheyney University's climate action plan. Secondly, we aim to develop infrastructure for the university that allows them to integrate sustainability and renewable energy into their education programs. And finally, we hope to engage the campus community in the sustainability of their campus and renewable energy overall. We ran into some constraints in designing this project. Having chosen not to develop a net metering agreement, we could not produce more than the daytime minimum load of the campus in order to not export electricity to the grid, which limited us to around 1 megawatt of capacity. The campus also has limited available space for potential solar and storage sites, especially on rooftop for roof-mounted PV. And finally, the campus already pays very little for electricity with their current agreement, making a financially viable PV and energy storage system difficult to propose.
Now we're going to move into our PV site system design. It is not forward on slides. For our conceptual design approach, we decided to shy away from rooftop PV due to the lack of available rooftops on campus, and we wanted to preserve the historical aesthetics of the buildings around campus. Our aggregate system data, we're going to have about a 1 megawatt installed capacity, or can produce around 1 gigawatt hour per year. If you wanted to look at the map here on the right side of the screen, on the south end of campus, the majority of our PV is in the geothermal field ground mount array that we've designed with about 750 kilowatts of installed capacity above the geothermal loop within the field next to the wastewater center. We also designed a agrivoltaics research site behind the Hill Library, which is going to work really well with the other alternative agriculture research being done on site with hydroponics and aquaculture. And then towards the west end of campus, we have our solar park near the new science center. And that's going to be kind of the jewel of our development. This is going to be a place that's going to be great for the community to be able to gather and engage in renewable energy and learn more as they go about their day-to-day lives. Our geofield ground mount system is located above the geothermal loop. As we stated before, next to the wastewater treatment center, it's got about 750 kilowatt rated capacity. And we chose to use the APA system's geoballast racking system, as you can see on the bottom side of our screen. And it uses a metal basket with any aggregate material to weight that can be found locally. It's not only going to bring down our construction cost, but it's also going to help us use the racking system to be commissioned and decommissioned easily when operations and maintenance need to be done on the geothermal loop below. And we also did a little bit of preliminary research and found that depending on the orientation of the loop underneath the ground, which we weren't provided, we could increase the summer efficiency during this if the geothermal loops are horizontally placed due to this extra shading on the ground. Our agrivoltaics research site is located behind the Hill Library, and it has about 148 kilowatts of rated capacity. We chose to use this site because we can offset the Hill Library's usage over a year almost entirely using this size array. And we think that the agrovoltaics research will be easily involved in campus in our biology department over there at Cheyney University with their agriculture research sites they have right now. We're planning on using a glulam wood board, which has a competitive price compared to normal solar racking with only a very limited increase in price of about 30 cents per watt. Our solar park is 112 kilowatts rated capacity, and it's going to use a very aesthetically pleasing racking system from the Brooklyn solar canopy, as you can see here below. And this space is less focused on producing the max capacity that we can. It's really going to be a place where the campus can get together and congregate for their events, or they can do graduation. They've done graduations out here, and we'll have a stage located in between the U shape of our arrays that they can use for events like that. And we think being able to see solar panels in your day-to-day lives and interact with renewable energies as you go about your campus career is really going to help make a more meaningful impact than having arrays behind a fence around campus. And we think this is something that's going to align really well with the university's master plan in order to get them more involved with renewable energy. And that's only going to be even larger when Sonali starts their manufacturing on Cheyney University's campus.
So for our battery, we chose to focus on the university's goal of resiliency for the critical loads in their new science center. So we began by researching PECO's outage history and found that it was pretty minimal. The utility is reliable. It regularly has a high safety rating. So with their 1 to 2 outages per year, they're never for more than a few hours at a time. And as such, we decided that 6 hours of autonomy was reasonable to maintain the critical loads inside for long enough to restore the grid. The battery system will sit next to the science center and charge from only the solar park array, since it's right next door and provides enough energy while avoiding unnecessary voltage drops and distribution costs associated with connecting to additional arrays. We ran a sizing calculation taking into account voltage, amp hour capacity, temperature coefficient, depth of discharge, and load, and concluded that the system will be made up of 16 24-volt 100 amp hour batteries, totaling to just over 34 kilowatts of storage capacity. The proposed system will be connected behind the meter with an automatic transfer switch that will island the building in case of a grid outage. Should the university choose to add this system, at this time it will cost around $9,000. That said, the price of batteries is projecting downwards and will likely be cheaper in the future. This graph on the next slide displays our energy storage scenario. The system will charge the battery as a first priority to keep the bank full in case of an outage, and then remaining solar production will be sent to the loads as a means of reducing energy charge. The blue represents energy drawn from the grid before the assistance of PV, and the gray represents after. As such, the blue shown that is visible represents energy saved from being drawn from the grid. This graph is framed to show general trends over a year, so the lack of blue in some places did not necessarily mean there's no PV being contributed. But in the beginning, as there is no blue showing, that is because all of the PV is going towards charging the battery initially. This would, of course, vary based on outages when the battery is discharged. So overall, this amount of energy saved is relatively small, but given that the original goal of the system is resiliency, that saving is an added benefit to the university.
And now for our distribution impact assessment. To minimize risk to the distribution system, we first ensured that our PV system power ratings did not exceed the hosting capacities of their respective feeder lines. We also minimized distances between our system components in order to minimize line losses. And we ensured that our conductors were properly sized to prevent overheating events. To inform our distribution impact assessment, we utilized the Cheyney distribution heat map, PECO's distributed energy resource interconnection viability map, and Google Earth place marks, polygons, and imagery. Overall, we assessed that the risk to the distribution system is low based on our array sizes and inverter outputs. Here you can see our selected layout for the geothermal field array. Our PV source circuits will feed into 450 kilowatt string inverters, delivering 600 kVA peak to a newly built on-site transformer. This transformer will then interconnect with PECO's distribution system. Here's our selected layout for the agrivoltaics research array. Our PV circuits will feed into a single 125 kilowatt string inverter delivering 125 kVA peak to a newly built on-site transformer. This transformer will then interconnect with Pico's distribution system. And here's our layout for the solar park array. Each 28 module solar canopy will be fitted with its own 10 kilowatt inverter. The inverters will feed into a subcombiner panel behind the event stage, and the output will be trenched to a multi-mode inverter, which will determine whether to charge the battery bank or send electricity to the on-site building transformer.
Moving on to our development plan. There are many associated risks that come along with the installation of large solar arrays or any electrical infrastructure that may be required for power distribution. The proposed photovoltaic installations at the University of Cheyney were designed to adhere to the codes by both the state of Pennsylvania and the Thornbury Township. These codes and zoning regulations govern all aspects of the project to ensure electrical safety, fire safety, and structural integrity. We will be designing and installing all the photovoltaic installations at the University of Cheyney in accordance with the International Fire Code, the International Building Code, the NFPA 70, which is the National Electric Code, as well as the 2018 Pennsylvania Building Code and the Thornbury Township zoning regulations. The University of Cheyney is located between both Chester and Delaware County, but the applicable zoning regulations do come from Thornbury Township. We'll be submitting a zoning permit, an electrical permit, and a building permit to the township. We did design all of our systems in compliance with the university master plan, with resiliency being our ultimate goal. There are many applicable codes we had to take into account when designing our system. The first two come from the 2018 Pennsylvania Building Code, stating that a clear brush-free area of 10 feet is required for all ground-mounted arrays, and that we must take into account axial and lateral loads when designing our embedded post and poles. The other ones come from Thornbury Township. They had many solar codes, but the ones most applicable to our system were that ground-mounted solar energy systems shall not exceed 12.5 feet in height and must have proper aisleways between panel clusters of at least 8 feet, and that DC-AC inverters should be installed at each cluster in addition to automatic disconnect devices. And to take a quick look at our construction schedule, we're going to be making construction happen this year to take advantage of the 26% ITC, and everything should be done by December 12th, as you can see here.
All right, so the Cheyney University use case was a unique challenge for solar PV due to the university's very low cost of electricity of about 4.7 cents per kilowatt hour. While the demand charge of $4.89 per kilowatt is significant for the university, any curtailment and evening grid demand from solar cannot be guaranteed each day, so the demand charges are left unaffected. Since Cheyney University is a public school, they are considered a tax-exempt entity and therefore cannot take advantage of any tax credits or deductions. After researching a variety of grants and incentive programs for solar PV, we found most notably that Cheyney does not qualify for the USDA REAP grant, nor does it qualify for the Keystone Innovation Zone tax credits. Since each of our three unique systems have a wide range of costs, we examined the financial needs of each system individually. This slide shows each of the systems as well as the combined system on the bottom row. It can be noted that the combined system price is higher than the aggregate of the three systems because it includes a construction loan, which we found to be consistent with projects of this size when a tax equity partner is involved. The final price tag of the project comes to $1.63 million with an apparent PPA of 7.4 cents per kilowatt hour. In order to make use of the $423,000 of tax credits that would be received from a system of this size, as well as additional tax benefits received from makers, we analyzed both a partnership flip structure and a sales leaseback structure to ensure effective utilization of these tax incentives. Both structures had similar IRRs and payment revenues, but the partnership flip had a much more consistent cash flow for the customer. Here you can see the PPA and sale leaseback structure from Cheyney's perspective, with the charts on the bottom showing the net cash flows for each year. While the payments and net present value for the customer are similar, the structure of the PPA versus the lease is quite different. For the PPA, the customer only produces revenue through avoided utility costs, and its only expenditure for the 20-year contract period is the PPA payments to the investors. However, during the post-contract period of years 21 through 30, the customer must pay to maintain the PV systems on its own. For the sale leaseback, the customer also can receive revenue through solar renewable energy credits in years 1 through 10, but they must pay to maintain the system for the entire 30-year lifetime, making the net cash flow more volatile. Due to its comparatively more consistent cash flow versus a sale leaseback, we recommend that the university pursues a PPA agreement with its investors. Over the system's lifespan of 30 years, our proposed PV system will cost the university a net present cost of around $250,000. We believe this cost deficit is more than worth the non-financial benefits of the system and its value as a novelty appeal, its addition to academic culture and coursework, and achieving the university's sustainability goals.